Hello, I'm Thomas Olson, and I'm going to make some videos on some polynomials. Anyway, I made these functions in my last video, and showed you how they relate to the ellipse. Today we're going to do polynomials. All you need to do is remove that, remove the denominators, and you got a polynomial generator. What you'll notice is that this function, I mentioned that these functions are similar to these functions, and these functions are from Francois Vieta, and they're not all that complicated to simulate the rotation matrix. All you need to do is put in 5 and arctan of x here, and that's like an x here and a y here. Whoops. Alright, so 5, we'll do 5 since everybody knows 5. Alright, what you're seeing here is a complex number. Whenever the computer sees this here, it does that Q thing that I mentioned in my last video, and puts it to the power of e or whatever, and I guess this is an easier way of putting it. Simplify. My computer's having some problems. Alright, well, I'll keep doing this video. If it continues to do these problems, I'll just delete it. Anyways, similar to this, you could put an x right here and a y right here, and you can get functions without the denominator. And if you really want to think about this, what we're essentially doing is we're putting a 1 right here. Hold on, actually it would be here. We're putting a 1 right here, and that's what's going on. Anyways, let's do this so it's a little bit more clear and solve. So we got 5 solutions. It's a degree 5 polynomial. 1, 2, 3, 4, and 5. What you want to do with this is you want to make another function. Well, a vector, I should say. Alright, so we put this in here. Making x1 and y whatever that was, and right here that's cos of pi over 5. That's sine of pi over 5. What I want to say is my polynomial or functions, they do pretty much the same thing. You put them in a vector just like this with the denominator x squared plus y squared minus x times y, or plus x times y, depending on if you're using x or g, or f or g. And just in the same manner, the ellipse is split into equal parts. Just the same way what we call them n-gons, but mine are not n-gons because they're an ellipse, and if they're an ellipse, the angles are all different, the side lengths are all different. The only thing that comes out the same is the area in each, well, for sure the inscribed triangle. Alright, so let's look at, we got an ellipse here. That length there is the square root of 2. This length right here is the square root of 6 divided by 3. To make this to do the standard form thing, implicit plot, we do this here. It's the same thing, kind of, it's just rotated. I don't know how to do implicit plot rotations. I guess this right here is part of the two things I mentioned up here. We put that right there. It's pretty much essentially the same thing, kind of, sort of. Alright, so let's talk about this. What I did was I rotated it, my vector, and I stretched it out right here and here, and there we go. It's pretty much the same thing. That's the ellipse that I'm talking about. That's the ellipse these polynomials are based on, and well, that's the ellipse that's part of algebra. It being part of algebra isn't the same thing as rotating an ellipse. Anyways, let's make some values here, if the computer will allow me to. Alright, fx, we'll make it 3. Let's do 3. Okay, we'll make x1, and we'll call y x, just so we have something that looks like a polynomial. And as I said, this denominator, we can get rid of it simply by killing the denominator up top here. The denominator really has no effect. I should point out, it's interesting that the PQ statistics thing that I showed in the last video, it's interesting that it has 3 ways of, well, at least 3 ways that I know of personally, of having a denominator, or some way of making, I don't know, whatever, who cares. Moving on. Okay, so we want to make a bunch of vectors, and we'll split this thing up, and what we need first are solutions. So obtain solutions. Now we got this thing here. Some of you actually may know what this is. They're complex numbers, obviously, and these are special complex numbers, in the sense that they have a 0 value, 0 imaginary value. This computer program can figure out what that imaginary, or what the real value is. In it's 2 times cos to the pi divided by 9 plus 1. And these other ones have similar answers. and those are in line with this expression right here. Alright, okay, I'm pretty sure that there's no way to express this in terms of the real value without the cos. The seventh, the heptagon, has a similar thing going on with it. I think there was a proof somewhere that said that you can't represent it in real numbers only. It has to have the imaginary component in the expression like this. Okay, so moving on, what we want to do is we want to stick this into here, and I do believe we're making x1. Now this, I mean, it looks pretty ugly, just the way it is, just because we have this thing here. Maybe this would be more interesting if we did this. Probably not. It's probably all gibberish no matter what. Oh yeah, that's worse. Oops, what'd I do? Alright, we'll just do this simplify. Yeah, that's not better. Anyways, let's plot it anyway. No, let's not plot it. Let's do 4 instead. And we'll just go straight to solve and see what happens. Alright, those are much easier to work with. Alright, so we'll do the +1. See what happens. That's a 1, that's a... And my cats are misbehaving. Alright, so... Alright, so we're going to do this to n, and we'll put in these. Okay, these need to be capitals, uppercase. We'll see what happens. Nope. How about with blots? Okay. Alright, so this was done to the 4th. What happened here is there are 3 times 4, which is 12. 12 in the upper quadrant and 12 in the lower, so there's 24 vectors here. And one of these vectors is 1, 1. I think it's that one right there. and we start from up here. We go 1, 2, 3, 4. That's how we find our vectors, right? So this vector here, I'm not sure where it is, but we could find it real quick. I think it's this one. There we go. So this one's 1, and this one's this is 1, comma 1, and this here's the first vector, and I guess let's see if it does it in order. No, it doesn't. Alright, why doesn't it do it in order? Well, it has to be this one. It has to be one of these two vectors in order to go 1, 2, 3, 4 across. So we start from up here. That's 1, 1. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's the 21st vector. That's what the vector should be right here. Nope, I did that wrong. Alright, so the first vector should be right here, this one right here. There, first vector right there. Alright, now let's walk around this. We'll do 12. What'd I do? Where am I? We'll do 12 of them. And the inscribed triangle here has all these have an equal amount on the inscribed triangle. I could show a few of them, I guess. I'll do that in a minute. We'll go to 24. So I guess that's good enough. We'll move on to the calculating. So we need the geometry, and we need to make this bigger so you can see what's going on. Alright, so we need a point at 1, 0 for starters. We need a point at 0, 0 for starters. And now we need to decide what B is going to be. B will be this first one, this first vector. Alright, this calculates the area, and that's what the area is. Okay, and move on to the next one. Alright, so we need to put this here. So we're going to jump back and forth between these triangles and see what happens. Exactly the same for that inscribed triangle. I hit the enter right here. Identical. Put that there. I approximate. Same thing. I'll do one more and then I'll call it quits. Okay. Do number 3. Simplify. Same thing. There we go. We could do an entire set of vectors just so you can see how nice these look, I guess. Make this a sequence. And we'll simplify it. Give it a moment. I do not think it's gonna be a quick evaluation this time, so we'll just say call it quits. All right. Have fun.